What does it take to measure a distance? Well, to find a distance, you need a starting point, an ending point, and a unit of measurement. Today we're going to be talking about the positions of those starting and ending points. We'll talk about the celestial coordinate system, that is, how do we determine where an object in the sky is located?
I feel like an astronaut in what you know about rolling down in the deep.
In the equatorial coordinate system, which is commonly used to name the coordinates of stars, galaxies, etc., Earth is at the origin. Why? Well, it's not because we're at the center of the universe, but as observers on Earth, it is convenient to use where we are situated as a reference point. But we actually have to be a little more specific than that. Whenever we define a coordinate system, we have to decide which side is right side up. By convention, astronomers often refer to the Earth's orientation on January 1st, 2000 at 12 o'clock terrestrial time. The x-axis in this coordinate system is the equinox. The z-axis is the Earth's axis of rotation, and the y-axis is 90 degrees from the axis of rotation. This is known as the J2000 reference frame. Over time, the Earth's axis will shift due to a process called precession, but this movement is so subtle that we only adjust our reference frame once every 50 or so years. Now, the ecliptic plane is the plane along which Earth travels around the Sun. The celestial North Pole is tilted 23.5 degrees from the ecliptic North Pole. Just like how latitude and longitude describe the geographic coordinate system, declination and right ascension are used to describe the equatorial coordinate system. Declination is the angular distance north or south of the celestial equator. It ranges from negative 90 degrees to positive 90 degrees. The celestial South Pole is at negative 90 degrees, the North Pole is at 90 degrees, and the equator is at 0 degrees. So how do we use declination to actually locate an object in the sky? Well, someone in San Francisco, California will be stationed about 38 degrees north of the equator. From San Francisco, if you look straight up, you will see the star Vega, since Vega also has a declination of 38 degrees. This point, the point straight above you, is called the zenith. If the observer from San Francisco wants to look instead at the Orion Nebula, where should they look? Well, the Orion Nebula has a declination of about negative 5 degrees, which means that it is farther south than the person in San Francisco. We simply subtract our position from the object's position. Negative 5 degrees minus 38 degrees equals negative 43 degrees, so the observer in San Francisco will have to look 43 degrees south of their zenith to view the Orion Nebula. By contrast, someone in Lima, Peru, is 12 degrees south of the equator, making their declination negative 12 degrees. Since the Orion Nebula has a declination greater than the declination of Lima, the observer will have to look north to see the Orion Nebula. Negative 5 degrees minus negative 12 degrees is equal to 7 degrees, so the observer in Lima will have to look 7 degrees north of their zenith to view the Orion Nebula. Right ascension is the angular distance measured eastward from the vernal equinox. The vernal equinox is the point where the sun crosses the celestial equator. This happens around March 20th. Right ascension is measured in hours, minutes, and seconds, where 24 hours represents a full 360-degree circle. That means 12 hours represents 180 degrees, and 1 hour of right ascension is 15 degrees. As the Earth rotates, stars appear to move across the sky. Like the sun, they rise in the east and set in the west. Right ascension indicates how far behind the sun a star is in its trek across the sky on March 20th, the time of the vernal equinox. So if an object has a right ascension of 4 hours, it will rise 4 hours after the sun rises and set 4 hours after the sun sets in March. As the Earth revolves around the sun, the time at which the sun rises and sets in each part of the globe will shift a bit. It takes 12 months for the Earth to revolve fully around the sun, so each month the Earth revolves 30 degrees. Remember, each hour of right ascension is 15 degrees, so if the Earth revolves 30 degrees each month, the time that a star rises and sets will shift by 2 hours each month. That means that a star that rose 4 hours after the sun in March will rise 2 hours after the sun in April. In May, it will rise at the same time as the sun. In June, it will rise 2 hours before the sun. This continues throughout the year until the next March, when the star will once again be 4 hours behind the sun. With these coordinates, declination and right ascension, we can easily locate various objects in the sky. So just to summarize, we always look to the sky from our origin point on Earth. But Earth is constantly moving, so we define our coordinate system based on the J2000 reference frame, with the z-axis pointing towards the celestial North Pole. We can find any point on the sky by knowing its declination, an angle between -90 degrees and 90 degrees from south to north, and its right ascension, an angle that is measured eastward from the vernal equinox from 0 to 24 hours. Well, that's all for today. If you like this video, please hit the like button or check out more videos. If you're confused by anything or want to put in a request for a future video, feel free to put in a comment below or reach out via email, which you can find in the About section of this channel. Thanks for watching!
Slow motion, yeah, I feel